Okay. Hope everyone can see my slide. Yes. Just write in chat
Yes,
box. Yeah.
yes.
Thank you. So yeah, a very good evening all. So welcome to the NPTEL online problem solving course for the course coordination chemistry, which is taken by Professor Devasis Ray. So myself Satyaprakash Yadav. I'm a PMRF scholar from August 2020 batch. Um, I'm working closely with Professor Satish Patil in SSU department, Indian Institute of Science, Bangalore. So about the course, so this is 12-week course. So in the week one, we have went through the introduction to the coordination chemistry, and and then we have discussed the different kind of classification of the ligand. Basically, in the three part class ligand one, ligand two, and ligand three. And then week two, we have discussed in detail like problem and solution and the nomenclature of the organic compound. And in week three, I will be discussed about the basically the coordination number of the organic coordination number of the coordination complexes. So if you have gone through the lecture number we have gone through the lecture number 7, 8, and 9. So, in coordination number 1, Professor has discussed the coordination in the lecture number 7. He has discussed about the coordination number 2, 3, and 4 in detail. And in the lecture number 2, he has taken the coordination number 4 and he has taken the different kind of complexes which has significant applications, something like catalysis, and he has discussed their structure and what is their structure, and little bit touch about the coordination number 5. And in lecture number 9, he has basically discussed about the coordination number 5 in detail, and here he has discussed the pseudo rotation in FeCO5, and he had touched little bit coordination number 6. And in lecture number 4, he has discussed the different kind of distortion in coordination number 6, and he has discussed briefly coordination number 7 to coordination number 12. So I will be just going through the different kind of problem one by one, and through the problem I will try to um, um, discuss the concept whatever you have learned in the from lecture number 7 to 10. So the first question is, how many different geometry have been observed in the metal complexes of coordination number 3? So anyone can write in the chat box which is the correct answer, and then I will go and discuss what are the possible like geometry for the coordination number 3. So I will wait 1 or 2 minutes just to see whether you can answer this question or not. Then I will discuss in detail. Okay, anyone else? Can you just look once again, because uh, there is a different answer for question number 1. Anyone else? Okay, so let me tell the what is the correct answer. The correct answer is 3. This one. So what are the different kind of geometry possible for coordination number 3? So first of all, this coordination number 3 is not very common for the coordination complexes. But what are the possible geometry can be there? I can discuss. So the first geometry what can be possible is the pyramidal. So as we know that for 3, just a minute. So pyramidal is like we have metal center M and we have oh sorry, so we have actually it's creating problem. So this is drawing a little bit horrible, but yeah, the first one is the pyramidal, which basically you have the tetrahedral. Suppose you have tetrahedral. So once you cut it one position, so that whatever we will get, that is the pyramidal. And other two are, so one is the pyramidal, other two are one is your T shape. So basically T shape, how you will get? So you have suppose uh, bipyramidal. So this okay, it's very horrible design. I am not doing. So this is uh, bipyramidal. Once you will cut these two ligand, so what you will get, basically you will get that is the T shape. And other one is once you cut it the cutting the two axial ligand, so you will basically get the uh, triangular one. So one is the, let me just write once again. So one will be your T shape, other will be your trigonal pyramidal. So basically it will be like this, and next one will be the pyramidal. So you have this. So the correct answer is how many geometry is possible is 3. Okay, so I think now you will got how many geometry possible in coordination number 3. Okay, so I will go to the next question. So BF3 takes the fluoride ion to form the BF4 minus. So here we have to predict the geometry of the both the species. So what will be the geometry for BF3 and BF4 minus? Can anyone just write in chat box? Okay, see, planar tetrahedron. Yeah, so you are correct. So I will just write the structure. So first BF3, it is like a triagonal planar. It's very horrible design I'm able to make because my laptop has one, right? So this BF3 will be the basically the trigonal. Okay, so here you have B, here you have F, here you have F, and here also you have F. And once we give one fluoride ion, so basically it will go to the tetrahedron. So what will be the structure? I will just write here. So this will be the structure for this tetrahedral. Sorry, this is going to here. So this is the fluoride. One fluoride is here. Okay, so yeah, you are right. So that is the correct answer for this. So now question is that what is the geometry and coordination number for metal ion in the copper 1 triazine 2 complexes? So option A is planar and 3, option B is square planar 4, option C is tetrahedral and 4, option D is T shape and 3. Can anyone guess what is the answer for this question? So again, this is the question from the coordinate number 3. Anyone? Okay, so let me go to that. So the correct option is the correct option is T shape L3. Sorry, T shape L3. How it will have just show. So this is the lecture where he has professor has told you about the triazine. So basically triazine is here. So once we deprotonate it, so one proton you will take. So here minus will come, and that minus basically if I write, so it's like this N double bond N, then here minus, and then you have here pH, right? So this can originate and it will go to the N minus single bond N double bond N. So this is, so basically your you can write it like this. So you have N N N. So basically you can just write it like this N minus. So this is the like N3, and we have the substitution here your pH, this side pH and other side also. So this is the triazine ligand. So what you will, once you put the triazine in the copper MECN4, you will get the Cu2 complex, which is of this kind. So here we have Cu N. Basically you are binding the 2 Cu with the N and N, right? So you wanted to bind this through N. So basically around one copper it will be like T shape. So if I see how it is T shape, so this is your T shape, basically T shape for this also we have the T shape. And coordination number is basically how many atoms bind to the that metal center. So this is 1, 2 and other is the satisfied through the copper. So basically your answer is that T shape, T shape and coordination number is 3. Okay, I think this will clear you the doubt. What is the geometry and coordination number of copper metal ion in Cu1 triazine 2 complexes. So basically here we have Cu2 and triazine 2. So this is the way it binds, and the shape is T shape. This is in the lecture number 7. So now the question number 4 is, what is the Wilkinson catalyst and what will be its geometry? Can anyone just write in chat box what is the Wilkinson catalyst and what is its geometry? Okay, the rhodium PPS3 Cl is carbon. Okay, can I ask one question? Here, like Wilkinson catalyst used for? Why it is so important, that rhodium complex? Can anyone just tell me what is the role of this Wilkinson catalyst? Oh, why it is so famous? Okay, so yeah, I think both the answer has come. I think Rupali, first you are correct. The correct option is C. So I'll just show you. Correct option is C. 1 minute. So correct option is C. So this is the rhodium complex found in the square planar. So basically you have this. Right, is coming. This. You have rhodium. You have pH. You have again pH, and other also you have pH. This is like Cl. I will just write 1 second here. You have rhodium, pH, pH. So you have pH and Cl. Okay, I'm sorry because I don't know why it's not working correctly. So this is the square planar. It's used for the yeah. Actually, my laptop has gone bad, so I'm using someone else's laptop and writing pad. That's why it's creating problem. Okay, so yeah, next time I will get it repaired, so it will not come. So I don't know why it's problem. So the correct answer is square planar. So once I think there will be one uh, somewhere this coordination equilibria is there. So somewhere once I will go to this complex, what is Wilkinson cartilage, then I will tell you people how like why rhodium complexes is in the like square. So the thing is that once you go to the down to the D uh, block element, you will see that square planar geometry get preferred over the tetrahedron. So that is the one reason. And second thing, once you will get once you have this D8 plus strong field ligand, that time you will find the square planar complexes. So this is the two thing you have to keep in mind. At what time you will get the square planar complex. So basically 5D and 6D prefers the square planar over tetrahedral. That is the first thing if ligand is strong field. Second thing is that if you have D8 configuration and you have a strong field ligand, so it will always follow the square planar. That I will discuss in the once we are discuss the crystal field theory. So there I will show you why this square planar is there over the tetrahedral. So I will go through from the octahedral, then I will go to the joint energy distortion, and then finally how square planar complexes we are finding, that I will tell you. So here the correct answer is rhodium PPH3Cl and square. And other thing, what is its role? So as already said, so basically it convert the sorry, it convert unsaturated alkene to saturated alkane. Okay, like this if you add the Wilkinson catalyst. Okay, yeah. So I will go to the question number 5. What is the metal ion present in the Vaska compound? Can anyone just tell what is the metal ion present in the Vaska complex? Yeah. Anyone else? Okay. Rupali ma'am is saying it. Okay, so let me tell you what is the correct answer for this. So your Vaska complex. So this is we have to remember what is the because complex name is the Vaska complex because Vaska is the scientist who has given that complex, which has affinity to find to uh, get a metal olefinic bond. So once Vaska complex, like Vaska complex will give the metal olefin complex once we treat with the ethylene. So what is the Vaska complex? So I will just write here. So we have iridium CO Cl PPS3 2. So this is the your Vaska complex where the metal ion which is present is iridium. So your correct answer is iridium. Okay. So basically it has tendency to find the metal olefinic complex once we are treating with the like any alkene like ethylene. Okay, so I will go to the next question. A square antiprism has geometry, has symmetry. What is the symmetry? It has a square antiprism. Can anyone just tell me? Oh, great. So can you tell me how you people are saying like it has D4D? What is the like symmetry element present in D4D? Can anyone tell me? Can anyone just write in chat box like what are the symmetry element present for D4D at least? Yeah, sure, I will just tell. So I think just 1 minute. Okay. So I don't have that slide, so I will just go through what professor has the slide at the end. So you just give me 1 minute. Okay. So where he has this. Yeah. So here there are, this is first of all it belongs to uh, uh, coordination number 8, right? So we have four possibility. One is the dodecahedron, cube, square antiprism, and hexagonal bipyramid. So as you know that hexagonal bipyramid. So we have this uh, trigonal bipyramid. So basically we have trigonal, metal in the center, and we have one up and one down. So for the hexagonal pyramid, bipyramid means we have a hexagonal plane, metal at the center, one ligand on the z-axis at top, another return. So this is the hexagonal bipyramid. And cube, as usual, we know that whatever we are sitting in the room, it's just a example of a cube where all sides are equal. So these, sorry. So if we consider, so these all sides are equal. So this is a cube where x means a is equal to b is equal to c and alpha beta gamma is equal to 90 degree. Now question is that how we will get the square antiprism. So what we have in square antiprism, we had two square faces and six trigonal faces. So how we will get it? So once if I like rotate one of the plane, this whatever we have this on top plane, if we rotate it by 45 degree, so what we will get a like a basically square antiprism. So next I think somewhere yeah, so this is the square antiprism here. This is the square antiprism. So we have, suppose this is the cube, you rotate this it by 45 degree, so this will come here and this will shift here, another will shift here, and one here. So we have only two square plane, one is the top, another is bottom, and all we have the six tetragonal faces, 1 2 3 and 3 from behind. So we have six trigonal faces and two square faces. Now the question is how you can say that it is D4D. So first of all, what is D4D? If I ask what is D4D, so first is that how we will define that whether it is D or not. So what is D? D is basically you have a dihedral. So suppose if you are writing as Dn, so we have basically Cn plus Nc2 perpendicular to Cn. Sorry, just give me a minute. Perpendicular to Cn. It's called Dn. So in this case, we have C4 axis and we have 4 C2 axis. Now, if I ask what is the Cn axis, what is the C4 axis, like what is the Cn axis? So basically, Cn axis is the axis from where if we rotate 360 by n, like if we have one axis, if we rotate by 360 by 4 means 90 degree, the complex will be remain same. So that is called your Cn, and we have perpendicular to that Cn, we have 4 C2, then it called Dn, right? Now what is this? Suppose if you retain D4H, D4D, like it's written. So how you will define that whether it is D4H or D4D? So D4H means if you have a horizontal plane perpendicular to the your Cn axis, so that is called D4H. Once it is called dihedral angle means your whatever plane is there, it should bisect the two consecutive C2. So this square antiprism, it is a little bit difficult to like difficult to imagine. So I will just take a very simple example. Suppose you take that your platinum. So I will just take a different slide where we have some space. So I will go to that question itself. Okay. Okay. So yeah, if you join next class, I can see that show you the 3D model. So okay, one more minute. Okay, I will just visualize you by okay how I can visualize. So see, you have this cube, right? You rotate that only top axis by 45-degree angle. So you will get, see, this is your bottom, 1 2 3 4, and this is the top which is rotated by 45-degree angle. You got it or not? So this is, see, suppose if you are writing, this is 1 2 3 4. So here we have 1 2 3 4. Now the top 4 we have to just rotate it by 45-degree. So this is 1 2 3 4. Whatever we have, 1 2 3 4 here. Okay, so any 3D model, I think I have to go to the YouTube and find out, because I have not taken from YouTube. So YouTube, there will be model available for this square integration. Okay, so I will take one very simple example. So I will just go back to the this one. Okay, so suppose I will just write it here. Suppose I take this platinum Cl4. We have Cl, 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 Cl. Now this is a planar molecule. You see, imagine one axis from the top, okay, in the z direction. So this is your z direction, this is x, and one is y. So once you rotate by 90-degree, what will happen? Your this Cl 1 2 3 4. Once we rotate it by 90-degree, basically 1 will become 2, 2 will become 3, 3 become 4, and 4 become 1. It's like exactly same like what we have. Okay, can you mute? Okay, so this we have C4 axis along z direction, along z direction. Okay, now we have C2. Suppose we take any line like this way. Can you see this line? 2 to 4. If we rotate it, so basically 1 will become 3, 3 will become 1. It's again same molecule. So this is one C2. We have other C2 this side, and we have one C2 this side. So basically if you rotate it along x direction, C4 becomes C3 and C1 becomes C2. If you have other like in y direction, so what will happen? Basically your C4 becomes C1 and C2 becomes C3 or interchangeable. So we have here C4 plus 4C2 perpendicular to the C4, right? So this is called D4, right? And we have one plane. We have one plane. Basically, your we have one horizontal plane. Basically, the plane like which is this one, sigma h, which is perpendicular to C4, right? So basically it is D4H. So like that, for square anti-prism, we have first D4, means we have C4 plus 4C2, and we have one dihedral plane which is bisecting the 2C2. Suppose we have one plane like this way, okay, and which will bisect the 2C2, then it will be D4D. Okay, so I will like upload, once I will upload in the like where that OneDrive, I will just give you what is the geometry and what are the all possible rotation possible in the like molecule, and then you can, I think, understand. Otherwise symmetry itself like a course, where you can learn like uh, what is all the operation, what is the how you find out the main axis, how you will the like principal axis, secondary axis, how it is CN, how it is DN, all those things you have to like uh, yeah, sure, you can see that record. Okay, now I will go to the next question. Okay, so why HG2 and gold 1 generally form linear complexes? Okay, there is one drive. I will this upload on my YouTube. That there you can find out. Another thing is that OneDrive where I will put my this slide also and the YouTube link. So from there you can go through the assignment 1, 2, 3, whatever I've discussed, and the that YouTube video link also. Okay. Now question is why HG2 and gold 1 generally form linear complexes? Yeah, already shared in that Google one. I think you will find out on the this NPTEL website. Okay, they have only sent it, and I'm just uploading there. Okay, so why HG2 and gold one generally form the linear complexes? Can anyone like tell me what is the answer for this? I'll just check once whether it is recording or not. Fine. Okay. Can anyone tell what is the answer for why Hg2 and gold 1 generally form the linear complexes? Anyone? Will wait for 1 minute. You people can think and just tell me what it is. They are bigger in size, so no d orbital participation. One furnace. Okay, anyone else? Okay, so let me tell. So the correct option is that B, participation of dz orbital in the bonding. So how? So I will just tell here. See how the dz square orbital is. It is basically your like in the z direction. Okay, sorry, this line is coming. So this is your along z direction, right? So this is the only orbital which is linear dz square orbital. So that's why like Hg2 and gold one basically it has dz orbital free. So that only can participate in the bonding. Okay, so basically here if you know that like if this is sp hybridization it will be linear, sp2 it will be either like coordination number 2, sp3 means coordination number sorry coordination number 4, right? So sp2 sp3 sp is linear, sp2 is sp3 is tetrahedral like that you have, so right. So this is the participation of the dz square orbital, because of that it is linear. Okay, so sd basically yes, and d mixture it will give two orbital which will bind along the z direction. Now what is the coordination number of this copper one in KCuCN2? I think this is the easiest question in the assignment number 3. Can anyone just quickly tell me what is the coordination number of copper in that? Yeah. So the correct option is 2. So what is the coordination number? So if I recall the Werner theory, Werner said that there are two kind of valency. One is the primary valency and secondary valency. So primary valency is ionic and satisfied by like whatever cation and anion we have outside the sphere. Secondary valency is the like non-ionizable and it is directional. So this is the 2Cn, like what is the number of ligand bind to the metal center is nothing but your coordination number. So there is a 2Cn bind to the copper, hence coordination number is 2. Okay, yeah, let me go to this. So mm, tungsten CO4 Br3 minus has geometry. So I forgot to put here 1 second. Why? It has geometry. What is geometry it has? Can you tell? Pentagonal bipyramid. Okay. Anyone else? Anyone else? Dodecahedron तो completely wrong, right? Because dodecahedron for coordination number 8, not coordination number 7, right? So what is the possible geometry for the coordination number? So first you see just what is the coordination number. So here coordination number is 7. So what are the possibility for the coordination number 7? First one is the capped octahedron. Second is the capped trigonal prism. And third is the pentagonal bipyramid. Yeah. So now the C option is already incorrect because it is for coordination number 8. Now for coordination number 7, 7 there are three possibilities: pentagonal bipyramid, capped octahedron, and capped trigonal. Okay. Now you have to guess and let me know. Okay. So let me tell you the correct answer is B. So I will just tell one thing. Like if you are seeing like when the pentagonal bipyramid will form. So if you see the complexes, suppose if you have something like this, metal x5, sorry, I will just write another way. It's very difficult to write here. M x5 Y2. So this will be favorable for the pentagonal bipyramid because 5 ligand can go on the pentagonal planar ring and 2 can go on Y inside like that, right? So this kind of geometry pentagonal bipyramid will only favorable where this kind of structure is there. Otherwise, it has go to the capped trigonal prism or capped octahedron. So in this case, this capped octahedron is there. If you want to know actually why, then we have to go through the like crystal field theory or ligand field theory only can help. Why this capped octahedron is there. So basically, we have to find out like where the energy stability, like the minimum energy configuration where we are getting. Or like in case of CF crystal field theory, how where is the crystal field stabilization energy is maximum. So that way we can find out like. But first thing is that like if I ask you like a question, one very famous example, VO AC AC2. What will be the geometry for this complex? Whether it will be the TVP or it will be the square pyramidal. Sorry, square pyramidal. So you will easily say that it is a square pyramidal because it's like your vanadium. Sorry, here I will write just here. Your vanadium will be here. AC, the 2O will be here, right? And one double bond will be here. So this is the most favorable geometry because it's more symmetrical, right? You can't say that it will be the trigonal pyramid like a prism because it has to then this what is O bond will be always in the strand. So you have to see that where the favorable geometry is. That's why you can guess the answer what will be there. Okay. Now the question is that in which types of distortion of octahedral geometry both X and Y are altered from the regular octahedron? Yeah, yeah. Square parameter is the correct answer. So I'm just telling how you can see that which geometry will be favorable if you have like ligand in such direction. Like suppose BO ACAC I have, so we have O should be go into the uh, DJ direction wherein the X and Y will be occupied by. That way you can just see. So if you go through the lecture, you will see this kind of trend. Okay. So now question number 10. In which types of distortion of octahedral geometry, both X and Y are altered from the regular tetrahedron? Okay, so it's be tetragonal elongation. Tetragonal, trigonal distortion, tetragonal complex. Any other guesses? See, trigonal distortion. Okay. Any other guesses? So if you are seeing be tetragonal elongation, so why not tetragonal compression? That will be also right. Okay. Yeah, correct answer is A. Now I will tell you how it is like a change. Okay. So what is tetragonal elongation and yeah, distortion. distortion, tetrarhombic distortion. Okay, so what is the tetragonal distortion? So basically, this is the John Taylor effect, which you will like come into that in week number 5 or 6, where we professor will discuss about the crystal field theory. So once you will read the crystal field theory, there you will come along the tetragonal distortion. So tetragonal distortion, what is that? Suppose if you have, I can't make good design here, otherwise can make. Okay, so you have this your octahedron where all the ml bond is same. Okay, now what you take, either you take two bond on the z direction up and this is down, both are just you move from the like you just elongate it, so that is called z out. Okay, jet out, or you just compress both the both the two ligand, that is called jetting. So this is tetragonal distortion, like one is the elongation, other is the distortion. So where only z direction distance, like ml bond in the z direction only will change. Now what is the tetragonal distortion, sorry, trigonal distortion? So trigonal distortion, what you have to do, you have to uh, do the elongation along the C3 axis. So I have one PPT, I will show you at the end. So there also you will not see the changes in the other direction. But what happens in the rhombic distortion? So in the rhombic distortion, what you have to do? You have to compress it along the z direction and elongate along the y direction. Okay, you have to compress it this one and elongate it along the y direction. So what will happen, your x and y will automatically will not equal. So if I write like, oh, 1 minute, I will just write here. So here x is equal to y is equal to z. This is your like regular octahedron. Now if you like in the z direction, what you do, you do the elongation, right? And in uh, z direction you do the compression, and along x direction or y direction you do the compression. So what will happen here, your x will not equal to y, not equal to z. That is your rhombic distortion case. Okay, so this is in D2S symmetry. So I have that PPT. You have already gone through that. At the end, I can just discuss in brief. Okay, so what are the geometry for NiCl2 Py2 and NiBr DIARS2 plus respectively? Can anyone just tell me what is the answer for this question? Can anyone tell what is the answer for this question? Anyone? No one? Okay. So the correct answer is, so see here we have like four ligand. So the what will the possible geometry? It will be tetrahedral, right? It will not be the octahedral. Now the question in the second, once we have nickel, we are DIARS. So what is DIARS? It is 1,2-bis dimethyl arsenobenzene, right? So we have two arsenic element which will act as a donor atom. So it is a bidentate ligand. So total we have here we have four. So I will just show you. Here we have four and here we have one. So now if I ask what will be the possible geometry? So total five. Either it can be the TBP or it will be the square panel. So what will be the correct answer? So I have already told you, like suppose if you have something kind of this one M X Y 4, right? So it will be favorable to the square pyramidal geometry. If you have something like M X 2 Y 3, then it will be favorable to the like tetragonal bipyramidal, because 3 will be in the plane and 2 will be on the z axis. So here what will happen, two die are whatever die bis die arsino that ligand is there, arsenic one, that will be on the xy plane and bromine will be in the z plane. So the correct answer will be tetrahedral and scorpion. Okay. Is that clear? Can I go to the next question? Okay. So, what ideal spectroscopy tool to observe the various pseudo rotation in FeCO5? This is again an important question. So, can anyone just guess? Now I have to move little bit fast. Can anyone guess what is the answer for question number 12? Hello? Hello? Any guesses? No, I am not getting any response. Okay, so let me tell you like which is the correct ideal spectroscopy for students. So what is the characteristics property for FeCO5? Okay, so this through the pseudo rotation it will go from TBP to square pyramidal. Okay, square pyramidal. So that we have to find out how it is going from TBP to square pyramidal. Now, what is the spectroscopy to determine whether it is in TBP or square pyramidal? Right? So the best way to measure that spectroscopy is your 13C NMR, right? So proton NMR we can't because there is no proton. IR will be the stretching frequency of CO. So in both the cases, CO frequency will be same. That UV spectroscopy, I don't think so any UV visible absorption spectra will change for FeCO5. But how, like it is good for 13C NMR. So in 13C NMR we have different kind of carbon attached to the iron center. So one will be in the axial CO. So once you will do the C13 NMR, you will be have like two um, and this. This will be the C axial and this will be C equatorial. So through this you can find out whether your like FeCO will be in the uh, TBP form or it is in the square pyramidal form. Okay, right? Now I will go to the next question. What is the ReH9 minus 2 has a symmetry? So first of all, we have to you have to tell me what is the like, first of all you have to tell me what is the ReH9 structure and then what is the symmetry. Can anyone tell the answer? No one. Okay. So so in Re, so your Re H time minus 2. So this is here coordination number is 9. Coordination number is 9 and the geometry is three phase. Sorry, this is it. Three phase centered centered trigonal prism. Okay. So this has symmetry of sorry. This has symmetry of D3H. Okay. So the correct option is D3H. Now can I go to the next question? So arrange the following complexes in the descending order according to the coordination number of the central metal atom. So this is very simple question. I think can everyone hear me? Okay, yeah. Can you just tell me what is the answer for question number 14? Arrange the following complexes in the descending order according to the coordination number of the uh, mm, central metal ion. 8213. Coordination number central order we have to write in the descending order. We have to write in the descending order. 5 second has highest side. Okay, so one thing you consider that NO3 has well, NO3 is a bidentate ligand. Can you consider it now? Mhm. Yeah. So the correct answer is B. One will be the highest, then three, then five. Because here four plus three, that is coordination number seven. Okay. So the correct option is B. So this is 8, 7, and 5. Now, question number 5. Which of the following factor is not favorable for preparing low coordination number of metal ion complexes? Can anyone just tell me? Anyone? If you have the bulky ligand, so basically you will be always go to the lower coordination number for the metal ion, right? Because you have more bulky ligand, so you have less space to accommodate more number of the ligand. So basically, which leads to the lower coordination number. But it is the question is which of the following factor is not favorable for preparing low coordination number metal complexes. So in the I think very first lecture he professor has told, yeah, the high oxidation state of the metal because it has very high polarizing power. So it will not allow you to more number to come closer more number of uh, organic ligands. The correct option is two. Yeah, correct. Now predict the coordination number and oxidation state of platinum in diamine dichloroplatinum. I think this we have already done. So coordination number is 4 because this is diamine means 2 to 4 dichloro 2 plus 2 4. I think you can easily tell like 4 plus 2, right? So this I will not go because in last week I have already. So now question number is this: what is the coordination geometry for the NiCN2 PPH OET2 3? Okay. Okay. 4. tetrahedral. How it is possible? Because we have coordination number 5, because 2Cl and 3pp, like basically PR3. This you write. This is nothing but I will just write otherwise. See, 2 is coming from here, and this is PR3 3. So 3 is here, 2 is here. So coordination number is 5. Then how it will be possible to D tetrahedral? Think that is wrong. So yeah, B trigonal bipyramidal. Yeah, that is the correct. So here again you see what is the kind of structure MX2Y3. So your all Y will be on the plane and 2X2 will be on the Z direction. Correct? So the correct option will be the this one. Yeah, trigonal bipyramid. In CLF3, the angle between the CLF3 FCF is are nearly equal to. Can anyone tell? First of all, CLF3, what is the shape? If you know the shape, then you can easily tell the answer. Oh, you are saying B. Can you tell me the shape? Yeah. So how? See, this is first. I will just tell you one rule. Okay. So do you have Cl? So you have to consider the number of bond and lone pair. So Cl have total two lone pair. Oh sorry. Why it is Cl has two lone pair and three bonding pair. Okay. Bonding pair. So it will be the trigonal bipyramid. So we have like one here, another is here. Sorry, this one F, F, F. Okay. So this is the sorry, this is the just simple you consider as single bond. This is single bond. So the rule is that lone pair will occupy the equatorial position. That is the rule. So if you cut the lone pair, basically you will get the same. So this is bent T shape. So if you consider one is nearly 180 degree and other two F are 90 degree. So the correct option is B. Yeah. Can we go to the number of denticity of the ligand triazine and acetate are? Triazine, I think we have seen in the question previously that copper complex with triazine, Cu triazine, then bracket 2. So what is the denticity there and what is the denticity for acetate? Can anyone just tell me what is the answer? Okay. For triazine, or acetate is 2, that is correct. Okay, I will just write the structure here. Oh, triazine 3 how? Because we have discussed now here the first question or second question we have discussed, right? Yeah, here. How many denticity is there? 1 and 2. 2 nitrogen only there to give the lone pair, right? That is 2 and 2. So I will just write. Okay. We have N. It's very problematic. We have N. We have N. Here we have pH. And here also we have pH. And this we have one negative charge. So this is your triazine, and one lone pair is here, another lone pair is here. So this can has denticity 2 And how we can write the acetate? I will just write CH3 COO. Okay. Now we can write as a this one. Minus will be onto 1 because once this has the OH, once you deprotonate it, basically minus, that minus can come here, and I will just show you. Suppose it has minus here. Okay, so that minus can come here, and that it found double bond and minus will be here. This is the routine use. So the correct answer is that 2. If a complex is NiX2 has triplet spin state, what will be the geometry of the complex? NiX2Y2 has a triplet spin state. What will be the geometry of the complex? Can anyone just tell? This, I think Professor has already given this kind of complex. I think we have come across also NiCl2py2 somewhere. Right? No. NiX2Y2. So if you have NiCN4, so that is the like uh, strong field like D8 configuration, then it will be in the like low speed complex, right? Then it will be the square bracket. D8, I will just write D8 plus strong field ligand. Strong field ligand. This will give the square planar. But here this is NiXY Y2 has triplet spin state. So the correct answer is the C, tetrahedral. Right? It will form the tetrahedral, but D8 it will be the low spin state. I will discuss the once we will discuss the crystal field theory. There I will discuss that why that NiX2 will be the uh, 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 tetrahedral. Okay. So I will go to the next question. What is the coordination geometry for NiCN2PP? I think this we have already discussed. This is the trigonal pyramid. Previous I have discussed this one. Which of the following is known as the Wilkinson catalyst? So this is just we have discussed previously what is the Wilkinson catalyst. Here that you have to tell me the IPC. Can anyone just tell me what is the uh, answer for this Wilkinson catalyst? Okay, so I will just tell you. So this is your rhodium EPS3 3Cl. Okay, so you have this is triphenyl phosphate. So it start with T, so it will come later. That chlorido start with C, so you have to write first. First is chlorido, then it has already tri instead, so we have to use these trees. So this is 3, so we have to use trees. So chlorido trees, triphenyl phosphate. Then this kind of ligand where they have already contained ditritenta, you have to write in bracket, and then what is the oxidation state of rhodium, that is one. So the correct option is this one, A. Okay. Now like AgNO3 plus the complex, this one is far not far because what is the reason? So the question is AgNH3 2 plus fat, but Ag ethylene diamine complex doesn't fat. Ag plus doesn't react with ethylene diamine ligand. The charge density is too low to bind with a bidentate ligand. Ethylene diamine cannot expand its bite angle to 180 degree to form linear complexes. In presence of bidentate ligand, silver extended its coordination number to AgEn3 plus. Can anyone just tell me the answer? Okay. So the correct answer is that so your ethylene diamine cannot expand its bite angle to 180 degree to form a linear complexes. Okay, that is the uh, uh, correct answer because see your these two can't be come in the linear and your CH2 will come like this because it's a tetrahedral uh, arrangement around C. So it can't give the bite angle to 180 degree to form a linear complexes. Okay, we'll go to the symmetry of tetragonal distortion is. Can anyone tell what is the symmetry for the tetragonal distortion? I will wait for 1 minute and then I will just tell what is the answer for this. Can anyone just write in chat box? No one? Okay. So the correct answer is C. I will just write it. Okay, D4H. So basically OH upon tetragonal distortion, what it will go? It will go to the D4H. And if you do the mm, rhombic distortion upon rhombic distortion, it will go to the D2H. Okay. And trigonal distortion if you do, it will go to the D3H. So that you have to see how it is going to D4H, D2H and D3H. Okay. So because this OH has already uh, 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 four four like 3C4, 4C3 and all those things it has. So that we have to see like what is the symmetry element for OH. Now once you are removing either Z in or Z out, basically you are uh, converting into D4H and rhombic distortion because only two plane is there, that D2H and trigonal it has trial, this is the D3. So these things you have to. Now in varying pseudo-rotation of FeCO5, the intermediate geometry is. What is the intermediate geometry? Can anyone tell? I will wait again 2 minutes and then 1 or 2 minutes I will wait. Anyone? In very pseudo rotation of FeCO5, the intermediate geometry is. What is the answer to this? Okay, so let me tell you. So what is the answer for this? That is the square parameter. So basically, it will be in first in TVP, then it will go to the uh, square pyramidal, square pyramidal, sorry, square pyramidal, and then finally it will come to the TVP. That is the very pseudo illustration. How it is happening, I will just show you how Professor has told. So yeah, this is. So first it is the TVP. Once you two equatorial one, you move in this side. So basically you will this all four, this 1, 2, 3, 4 will come in the plane, and this will be the square bipyramidal. And once these two will move this side, so basically you will get the trigonal bipyramidal. How? Because now once you move these two, then 1, 2, 3 will be the like once you move these two in that direction, so basically this is the z direction, and 1, 2, 3 will be the your e- equatorial position. So this way it will start from TBP to TBP through a square bipyramidal intermediate. Okay, so here this is the correct answer for the this one in very pseudo rotation. What is the efficient? Now the next question is, which of the following geometry is not possible for coordination number 7? Can anyone just tell? We'll just wait for 1 minute. Anyone? The first is pentagonal bipyramidal, capped trigonal, square anteprism, and capped octahedral. Anyone? Okay, so let me tell you. So this we have first. I will try the pentagonal bipyramidal. So we have pentagonal plane, and then we have two on z direction. So this is total. That coordination number is 7. So this first one is uh, already for the geometry. Cap trigonal prism. So trigonal prism is for the coordination number 6, right? Only this coordinate trigonal by prism. Once you capped it, so basically it is 6 plus 1, 6 plus 1, that is 7. Again it is for the coordination number 7, and cap the octahedron. So octahedron is coordination number 6. Once you capped it, 6 plus 7, 1, 7. So this is also correct. Square antiprism. That is the correct answer, like geometry which is not possible for coordination number 6, because it is the geometry for coordination number 8, where we have 4 ligand. Basically once you have a cube, you have one cube, you rotate the top this plane by 45 degree, so you will get the square integration. So here we have 4 ligand and bottom and 4 ligand and top. The top ligand will be the rotated by 45 degree. This one the correct. Now the next question is geometry of the complexes W C O B R 3 and BR3 minus and Z dash OXR. Okay. So this WCO4 BR3 minus, this one I think I have already told you is 7, right? So okay, this I think I have already told you. This is total 4 plus 3. So total coordination number is 7. So your this will be the capped octahedron, that is the first, and this is zirconium auxiliate. So this kind of complexes will form the, so here coordination number 8. Coordination number is 8. So what will the possibility, whether it can be the dodecahedron or square interprism or hexagonal bipyramid or cube. But the, if you see that zirconium and all other complexes will form the square interprism, which professor has already told you. Okay, so these are the things where like what professor has told in the coordination number 1 classes and coordination number 3. Okay, so this I will just share in the like I will share these things in the whatever that sheet is there. Okay, so let me start the recording now.